Hello everyone and welcome to today's webinar, Phase Change Materials. How can they help set your company apart? Presented by ATP member Alexium and brought to you by the Advanced Textile Products Division. ATP represents the safety, medical, and interactive textile product marketplace. ATP also offers sponsored scholarships to support the future of the industry. The division provides a forum to exchange information, solve common problems, and develop mutual beneficial relationships. Before we get started, I would like to go over a few items so you know how to participate in today's webinar. You will have the opportunity to submit text questions to the presenter by typing them into the questions box of the control panel. You may send in your questions at any time during the presentation. I will collect these and they will be addressed during the Q&A session at the end of the presentation. The PDF of today's presentation is currently available for download under the Handouts tab of your control panel. A link to download this PDF will also be emailed to you later in the week. Now I'd like to introduce today's presenter, Dr. Robert Brookins. Dr. Robert Brookins is an interim Chief Executive Officer at Alexium. Previously, Dr. Brookins worked as the company's Vice President of Research and Development. He has more than 15 years of experience in organic synthesis and material chemistry. Prior to joining Alexium, he worked at the Air Force Research Laboratory, where he performed research related to chemical and biological warfare agents and material applications. At Alexium, Dr. Brookins and his team pioneer new classes of flame retardant for key textile markets. Additionally, his research focuses on phase change materials, particularly novel application methods and analytical tools. Please welcome Dr. Brookins.
Thank you everyone for joining us today, and thanks to IFAI. I appreciate the opportunity to talk with everyone about applications of phase change materials and hopefully to help give you some insight in terms of how you can best use them in your work. You know, textile applications of PCM as it continues to increase and expand. But interestingly, unlike other technical textiles such as flame retardants or oil repellents, the metrics for product design and quality control are not well defined. As a result, the past decade for PCM treated products has largely been driven by marketing. Something I laughingly discuss internally here is that the past 10 years has largely been about how many blue snowflakes you can place on a plastic wrap or how many names you can use to suggest ice and cold. While that has worked in the past 10 years, I think what you now see is that does not provide a route to a well-differentiated product for yourself, and something that can well differentiate you from competitors. Hopefully this webinar can provide some basic insights into phase change materials and help you gain a better understanding of how to use them. To look briefly at what we'll go through. First, I want to talk about background on phase change materials. Really want to try to keep this simple, but a basic understanding of the physics behind phase change materials will dramatically impact what insights you have in terms of how you might be able to use them for your applications. We'll then focus on thermal management with textiles and talk about what are the balance of properties that you need to consider when working with phase change materials, and also just thermal management with textiles in general. From that, we'll do a general review of thermal analytical methods for PCM versus other thermal properties, as something that Alexium has been very focused on over the past few years is how do we best understand what is the performance value of phase change materials and how do we discriminate that relative to other thermal properties of the fabric. That has led us to the development of our Alexium EC method, which is specific for PCM treated textiles. I want to give you a bit of an oversight in terms of what the value of that is and how that can be used in work related to product design and quality control. Now, first one is just basically start with the basics of phase change materials. Frankly, without understanding these, the process of developing a product that you want for your customer or that you would like to have, that you want to be a part of, you can ultimately end up with an unsatisfying product. And I think that what's important to make sure that you don't get in that position is to understand some of the basic properties of phase change materials. Now, basic background on phase change materials. Since its inception in the late 1980s, PCMs have been increasingly used in a wide range of markets, including textiles. Over the past decade, PCMs have been one of a number of different methods people have used for thermal management technologies with textiles, and we'll discuss those in the second section of our webinar. Some of the areas where PCM materials have seen use in textiles obviously is with apparel and mattress components, meaning actually part of the mattress, and then you have top of bed of accessories such as pillows and blankets, and increasingly those are an active area for PCM applications. Now, first, I think we really have to start with what is the most basic part of this. What is meant by phase change? And unfortunately, we really have to go back to the beginning, kind of a basic level understanding of materials. And that is that when you're talking about matter, obviously we can have solids, liquids, and gases. This is something that's familiar to everyone. Now, when we're talking about a phase change, all we mean by that is that you're converting the material from one state to another, from a solid to a liquid to a gas. The most obvious place where you have everyday familiarity with this is when we talk about water. Obviously, we can have water in solid form as ice, all the way up to a gaseous form as steam. Now, the key point here is that when we're looking at what is driving this transition from one phase to another, as you go from ice to water and water to steam, what's driving that transformation is that you're adding energy into the system. And this becomes the basis of any application that you would have for a phase change material. And what's important here is the quantity of that energy. It's a significant amount relative to what you would see with other processes, such as when you're just heating up a material. Now, to briefly delve into what is happening with this, we need to talk about what's happening on a molecular level. So when you have a material that is in a solid form, you have the molecules within that material are interacting with each other. You have forces that are helping to hold that together. What's happening once you go through a phase change is you're now providing enough energy that it goes from a solid form to liquid form. The molecules or atoms have greater mobility relative to one another, and now it's fluid, and it can will adapt to the form of a container and has all the properties we know of as a fluid. Once you add then even more energy, that takes it to a gaseous form. Now, a key point here is that this process is reversible, and that's something that needs to be considered when you're talking about phase change materials. Yes, it does absorb that energy, but also that energy will ultimately get released back into the environment based on the temperature. Now, this is not something that's important to keep in mind when you're talking about a phase change material, is that what determines when you move from a solid to a liquid or liquid to gas is what temperature you're at. That's what's driving that transformation. Obviously, we know this already. We're talking about ice melts to a liquid at 0 degrees Celsius and water turns to steam at 100 degrees Celsius. The key point to recognize here, and I touch on 3 key points you want to keep in mind through this webinar, is that when a material reaches that phase change temperature, energy goes into it, but does not raise the temperature. This might sound a bit, conceptually hard to understand, but really from your day-to-day experiences, you're very well aware of this, because when you're talking about all the energy that goes from converting from a solid to a liquid, this is something that you're very familiar with when you're talking about using ice. So I'll give you basically a thought experiment that can help you understand what that key point means. If you were to take an ice cube and put it on an oven that's at, imagine a pan that is sitting on a stove, and it is at 100 degrees C, and the ice is sitting in the middle of the pan, melting and starting to move around. If you were to pick up that ice carefully, make sure you don't burn yourself, but pick up that ice cube, the ice is still 0 degrees C. It's still ice. What has happened is the heat from the stove has gone, the energy there has gone into transforming that ice from a solid state to a liquid state. Yet the ice itself has not increased in temperature. That's the key aspect of what you have there when you're working with a phase change material. Another example, just to touch on it, is that's obviously the purpose of when we put ice into a drink. When you put ice in a drink, you're helping to keep it cool right there close to 0 degrees C. And as the environment starts to put energy into your drink, rather than making your drink hot, what it actually does is the energy goes into the ice and converts it from a solid to a liquid. And that helps to maintain the temperature of the drink. Any type of phase change application, it's these type of effects that you're looking for. Now, the next slide, what I really want to give you a sense of, and this is after this, we'll begin focus more on textile applications, but I want you to have a sense of different ways in which selection of the phase change material can impact what type of properties you're going to get. Now, typically for textile applications, you'll be using a paraffinic material, a wax type material that is but of notably high purity. Now, what we have listed here is 6 different waxes that would be commonly used, be considered for textile applications. Don't worry about the first 2 columns. I really have that there just for people who want to have that as a reference. What really matters is the melting point and the heat of fusion that you see there. First, talk about the melting point. As you can see, we have something like the top material that is melting below room temperature. And so that's something that if you already had it at, if you were to have an application that was to be at sub-ambient temperatures, once you get down into, obviously cold environments, that type of phase change material would be more applicable and could have a desired effect depending on whether you want it to help cool or warm a person. The most common material that people use is octadecane, which is at 28 degrees. And the relevance of octadecane is that at 28 degrees C, you're in between room temperature and body temperature. So what ends up happening is when you touch a material that is treated with a phase change material like octadecane at that temperature range, you're going to have a cooling sensation. The temperature from your hand goes into warming up the octadecane and then melting it at 28 degrees C. And then instead of it feeling warm, it keeps that same low temperature as opposed to going up to body temperature. Obviously, you can go to higher cuts of higher fractions of the wax, going up to as high as 40 degrees C, and you can go well beyond. But if you're talking about textile applications, typically for the markets that are relevant today, apparel and bedding applications, these are the type of range that would be of interest. Now, in terms of the other column that you want to look at here is the heat of fusion. And I understand that's a complex sounding term and not something that is very common, but it's really just a very simple idea. What this value tells you is how much energy would 1 gram of this material absorb. And you can see here the numbers for these phase change materials range from 170 up to 247 joules per gram. For a little bit of perspective there, if you think about a typical fabric as you might use, polyester, even a ultra high molecular weight polyethylene, as that fabric was to warm from room temperature up to body temperature, you would absorb somewhere around the mid to high 20s in terms of joules of heat. In contrast, you have these phase change materials that absorb in the hundreds. So there's much more heat that can be absorbed by a phase change material as opposed to a fabric as it warms from room temperature to body temperature. Moving on to the next slide, I won't delve into this to any great degree, but I think it is nice to have some perspective of what is the range of markets that phase change materials are used in, not simply in textiles. What you see, this is from a marketing report that is available. On the x-axis, you can see the market share that these different markets have. PCM has, the different percent PCM usage relative to each market. And then on the y-axis, you have the CAGR, which is telling you what is the anticipated growth over the next 10 years. You can see that textiles, while they are PCM is widely used in textiles today, it actually represents a relatively small share of the total markets that are currently used. Primarily, they're used for HVAC, shipping, and building and construction. But also, you can see that a lot of more significant growth is anticipated for textiles opposed to others. Now, one other point that you want to talk about for phase change material, especially for textile applications, is that typically you would want to use PCMs as in a microencapsulated form. Because most PCMs are based on a solid to liquid change, microencapsulation is needed to prevent leakage of the liquid. So what this looks like, in case someone is not familiar with microencapsulation, it really is very similar to what you would imagine for a capsule as you might have for medicine, where you have a outer shell that contains some active ingredient inside. That is the exact same thing that you're doing with a microencapsulated PCM, except, as the word micro implies, this is actually happening on a much smaller scale. This is an image of a phase change material application that we have on textiles, and you can see that the particle size for the microencapsulated PCMs are in the range of typically 5 to 20 microns. Some get a bit larger, but it is definitely on the size scale of the fibers themselves. That's also one thing, if you're talking about textile applications, it is one point to consider if you're not wanting the PCM to have a frosting effect where it has a whitening due to the particle size. And that's something that can be tailored depending on the application that you have. Now, next I want to talk about thermal management with textiles. And from here, we'll really focus on textile applications solely. Now, when you're looking at the value of thermal management in textiles, I've pretty much narrowed it down to there's two basic reasons you would want to use a PCM or other thermal management technology on a textile. One is you simply looking for that cool to the touch effect, as you see as is used with mattressing and pillows, and where you have that dramatic impact. We call it the pop of the coolness whenever you touch it. But also another important application of PCM and other thermal regulating chemistries is where you're actually trying to control the temperature of the environment. This is what drives building and construction applications. That's absolutely what they're looking for there. But in textile applications, this is increasingly a focus where you're looking to manage what is the temperature of, say, of the mattress or the apparel when someone's wearing it. So here I have a video which will show you a demonstration of the cool to the touch effect, which is a significant part of the market applications that you currently have. Now in this video, you can see that what I've done is taken a competitor's pillow shell, which has been treated with PCM, and on the bottom portion is an Alexium treated pillow shell. And you're going to see in this video to the right where we're laying our hand across that both fabrics, and then looking at the temperature response by using thermal imagery. I think as you'll see in this video, you can clearly see that by carefully controlling the amount of PCM that you're applying, you can have a dramatic effect on the temperature of the fabrics. For this particular pillow shell, on top, there's actually a relatively low loading of PCM. Toward the end, I'll give you some analytical work we've done looking at these, and you can see how much more this fabric warms up relative to a product that Alexium was working on. Now, something that is absolutely imperative to consider when working with PCM applications on textiles is that while PCMs will actually absolutely help you in thermal management and getting that cool to the touch effect, it is actually only one of a number of different properties that will contribute. Everything from the air permeability of the fabric, how the fabric is constructed, the fabric weight, thermal effusivity, and moisture wicking. All of these are going to be contributors to what is the final thermal management effects that you have for the treated fabric. And frankly, you can't look at any one in isolation. You really have to look at how they all work in concert. Now, to focus briefly on phase change materials and moisture wicking, I think it's important to understand two key properties around both of those when you're looking at different applications of these. I typically refer to these as active thermal management chemistries because you have some mechanism that is allowing you to drive the cooling of the fabric, or well, here we're focusing on cooling, but to drive the cooling of the fabric. For PCM, you also could look at it for heating applications, although we won't discuss that in any great detail. So when you're looking at phase change material, what is happening here is you have up here on the top of the of this yellow square, you can see a microencapsulated PCM where the PCM is now in a solid state. As the temperature rises, the PCM will absorb that heat, and then that absorption will result in the PCM going from the solid form to the melted form. And then it is in that liquid state. Now, what's important to realize is that energy has not gone away. PCM is not going to violate the law of conservation of energy. It still is inside that PCM. And as the temperature begins to fall, ultimately that heat is going to be released back into the environment. So that's the second key point to keep in mind. PCM absorbs heat, but the heat doesn't disappear. It's simply stored. And when you're thinking about applications of PCM for products that you're designing, that's a key thing you have to keep in mind. And ultimately, the PCM will absorb a certain amount of heat, and then it's reached capacity. Now, when you're talking about evaporative cooling, what we're dealing with here, this is separate from PCM, but I think these two are frequently confused in the market, especially when we look at how people are marketing the materials in stores. Evaporative cooling works by once the fabric begins to gather moisture and it gets wet, capillary action will wick the moisture throughout the fabric, and it will help to through a sweating type process as it goes from solid to liquid state. The water will evaporate, and that helps to cool the fabric, exactly in the same way that sweating does with your skin. An important thing to consider here is that these cooling effects are only active when moisture is present. So when you're talking about sportswear applications, absolutely the evaporative cooling through wicking chemistry is a great fit. If you're talking about bedding accessories and things of that nature, it's not such a it's not as good of an option, simply because the presence of moisture is going to be relatively low. Now, there are a number of different methods of applying PCM to textiles, and as we show here on the right, basically any standard method that you would anticipate using for textile chemistry is generally available. I know we've done everything from pad nip, screen print, knife coating, spray, foam applications, and then you have PCM suppliers, particularly Outlast works with infusing the PCM into the fibers. An important thing that I want to draw out here is that when you look at two different application of PCM onto fabric, you can see that while in both cases we're applying the same PCM, the overall effect on the textile is very different. On the top, you see a spray application of the PCM, and on the bottom, you see a knife application. Now, it's basically a give and take here. With the knife application, you get much better coverage of PCM, and the overall cooling capacity that you're going to have from that application is going to be great. On the flip side, though, you're going to have lower air permeability, which is something that needs to be taken into consideration in terms of the final overall performance of the fabric. In contrast, the spray application, not as good of coverage. You're going to have a lower overall PCM level, but the air permeability is going to be significantly improved because you're leaving gaps to allow for airflow. Looking for that balance of those different contributors to thermal management really has to be taken into consideration. And that was my point. This is a great example of the point I was making back on the title slide. If you're not weighing all these factors all in balance, you can end up producing a product that ultimately you're not going to be happy with. Now, the considerations obviously go much beyond thermal management, and there's a lot of different properties that you'll want to take into consideration that I want to touch on briefly. Obviously, you need to look at the coating effects. We've talked about been focusing very much on thermal management, but if you add a PCM application for bedding that ended up giving it a very hard, stiff hand, then that obviously is not going to be acceptable. And that's something that can be tailored as you go from one application method to another, and also looking at the secondary chemistries. Also list here transparency. That means transparency of the finish that you're applying. Basically, selection of the best particle size can is really what would be needed there to tailor that. Multifunctionality is something that is also want to look at. The flame retardant applications is something that is generally needed, given that you're adding a waxy type material for something like bedding. You'll need a flame retardant that can be incorporated in with your PCM to help counterbalance whatever additional flammability it may be introducing. You can also add water repellent and antimicrobial. Integrating these into a one-step process can be done. That's something Alexium has done a great deal of work on, but it does help to minimize the ultimate cost for a given manufacturer. We've already talked about application methods, so I think we're good there. A key point that typically comes up toward the end of discussions around PCM applications, unfortunately, is commercial viability. Because while we can focus on what is the best PCM application to get a desired effect, also need to take in consideration, is the cost reasonable? Or for a given PCM type you're using or secondary chemistries you're using, do you end up introducing materials that are bad about releasing VOCs or formaldehyde? That's something that definitely has to be taken into consideration and want to consider in early stages as opposed to late stages. To briefly touch on the VOC versus trying to maintain low VOC and low formaldehyde, most of the shell materials that you would use for a PCM are what's going to drive this. The two most common materials are acrylic shells and melamine formaldehyde shells. Typically, the acrylic shells are going to be more apt to release VOCs. The melamine formaldehyde obviously would release formaldehyde. So it's a bit of a give and take there in terms of what is the best way to go in terms of commercial viability. And it's just something that will need to be managed. Finally, you obviously have the product's chemical properties to make sure that it's acceptable for use, such as getting certification for that is ecotox friendly. Now, what we'll talk on for a bit here is talk about major textile markets where phase change materials are used. And we touched on this briefly, but I think it's worth going into a bit more detail regarding the individual needs of these applications. So if we talk first about apparel, sportswear is where thermal management has been most widely used, but this has predominantly been done with wicking chemistries as opposed to PCM. This is probably a bit obvious given the fact that considering that for sportswear, the moisture that would go onto the fabric as a person begins sweating makes the wicking chemistries just an ideal fit for that. But in terms of looking at integrating PCM applications, it absolutely can have some role there, especially looking at how you can integrate different types of PCM and how those different temperature ranges could be valuable in terms of providing a cooling effect. Something to keep in mind here that I would like to emphasize is that when you're talking about sportswear in particular, you really have to take in consideration wash durability. And this is a real challenge whether you're dealing with wicking chemistries or with PCM products. Alexium developed a PCM wicking combination where we applied both types of chemistry in one step. And getting the performance we needed was relatively easy, but attaining the wash durability was not. It was something that did take a great deal of work. Ultimately, we achieved 50 wash cycle launderability, but only with significant amount of investment on research side and also close consideration of what exact type of fabric we're dealing with. So in terms of the challenge for phase change material applications in sportswear, that's clearly the greatest one. In terms of PCM applications for medical staff, this is much more varied in their needs, and it's about really what type of benefit they're looking for. And in terms of, it's not as easily characterized as what you see with sportswear, but it definitely is an area that we have heard of increased interest, but is a more complicated needs, and from what we're seeing is not as critical to work out the wash durability requirements based on the needs for those medical garments. Now, one of the more widely used applications is in the mattress industry. It has really been application of PCM to the mattress components has driven a great deal of the growth that you've seen in this industry, and still a great deal of innovation is going on there. We see that continuing well into the future. Given the complexity of mattress design and selection of fabrics as well as selection of PCM materials, there's a lot of a great deal of innovation and technical advances that we see are still going to be you're going to see over the coming years. Another area that is of interest, obviously, is bedding accessories such as pillows, blankets, sheets, anything that would be considered top of the bed. Obviously, if you look in the big box stores, this increasingly takes up. You see these on the shelves, and I think it's going to be a growing market. And right now, it's lagging behind what you see in mattressing. but has the is definitely going to be a big area of growth over the next 5 years. You do have touch on durability, which is something that always has to be considered. Typically, a 5-wash launderability is what would be required there, but for different applications, especially like with sheets, it could be much greater. Now, next, I'd like to touch on a review of thermal analytical methods for PCM versus other material properties. Now, I think the complexity here that we have dealt with as Alexium has got increasingly worked in PCMs for textiles is that characterizing the performance of the PCM and really being able to understand what part of thermal management it is directly contributing as opposed to what the other properties are doing, such as air permeability and fabric weight. That really is a very frustrating thing to have to be able to work out. And so in the early days, we reviewed a number of analytical methods to see what the options were. And I want to do a brief review of different type of analytical methods that you may have seen either in the literature or used by people in the industry. Now, we have seen are 3 general methods that have been used to study phase change materials. And what we're particularly looking at here is not simply saying, does the PCM have an effect as would be measured by guarded hot plate? But we're really trying to look at is, what is the effect the PCM is explicitly having? And how do we use this method as a means of driving product design? How does that guide quality control measures? What does that enable you to do in terms of marketing claims? So we're going to dive in here and look at these different methods and basically dissect what is the advantages and disadvantages of these for looking at PCM applications. Obviously, the guarded hot plate is a standard method used for thermal properties of textiles, particularly as it relates to comfort characteristics of garments. Importantly, the enthalpic cooling or cooling capacity of the PCM is not something that you're directly measuring with this method. And what you're actually measuring is the Clow value, which is the thermal resistance, also evaporative resistance, and the total heat loss. Now, when you look at the design of the guarded hot plate method and how it's used, there's 2 key aspects of it that basically guide you in seeing that it's really not an ideal method for looking at what is the effect of the PCM on the performance of the textiles. First, as used by a standard method for guarded hot plate, the heating elements are maintained at 35 degrees C, or could be at a different temperature, but this is a standard temperature. And the data collection begins after the fabric or fabric assembly reaches steady state conditions. The problem here is, while you're waiting for this fabric to reach steady state conditions, the PCM is going to be absorbing that heat. And by the time steady state conditions have already been reached, you've now exhausted what thermal effects the PCM is going to apply. So, as a general rule of thumb, looking at a test method that works under steady state conditions, it is just generally it's not going to work well for phase change materials. Also, as anyone who's familiar with testing around the guarded hot plate, the measurements are critically influenced by a wide range of factors, including the air permeability, fabric weight, other finishes. Basically, any material change that you're going to make to that fabric, you're going to see that impacted on the guarded hot plate. Excuse me. So discriminating the effect of one variable versus their collective effect is not really easily done with a guarded hot plate. Now, there have been some people who have looked at non-standard methods of how you might use a guarded hot plate. This is one study that I pulled here from a few years back. And in this study, they looked at the effect of the PCM, the effect of the binder. And as you can see here, as we're looking at different loadings of PCM versus different loadings of the binder that was used along with that PCM, you're seeing the same basic effects regardless of which property you're looking at. So guarded hot plate, whether in a standard or non-standard method, we've seen has traditionally not been fruitful in terms of looking at the effect of PCM on textiles. Now, another method that has been fairly recently introduced is looking at thermal effusivity as would be measured with the C-therm equipment. Now, this equipment provides a quantitative measurement of thermal effusivity of woven, knitted, non-woven fabrics, really can be used across a wide range of materials. The best way I would explain the value of the thermal effusivity measurement is not focus on PCM materials, but actually look at a different type of experiment. If you were to walk into your kitchen where everything in the kitchen has been sitting there undisturbed that day, and you were to grab a metal spatula versus a plastic spatula, the plastic spatula is going to feel not necessarily cool, just effectively, room temperature. On the other hand, a metal spatula will feel very cool. That's because of the high thermal conductivity of the metal. You're getting this cooling effect as it's pulling heat away from your hand. That is not a phase change type process. That's simply a reflection of thermal conductivity and ultimately the thermal effusivity of those products. So when you're looking at cooling performance around these type of two different materials, C-therm that's really what it was designed to do. Now, Alexium did a third-party study where we looked at different fabrics to see what is the impact of a phase change material on the treated fabrics. Now you can see that on sample A, where we have 17% PCM, the average effusivity that was measured was 165, but this has a significantly higher effusivity than a sample that has 29% PCM, which is sample B. In comparison also, you have sample C and D, which shows that even though we're adding chemistry, we're doing this through a acrylic binder, even though we're adding chemistry that is not PCM, you still see a significant change in the average effusivity, which ends up being between what you had in the grayish fabric and what you had with a PCM-based fabric. So you can see that this method doesn't allow you to discriminate between the loading of the PCM that you have, and even not having PCM directly impacts the type of effusivity measurements that you get. In a nutshell, I think it's worth saying that the type of data you're going to get from using a measurement of thermal effusivity is going to be similar to what you see with the guarded hot plate, where you have contributions from all of these different fabrics, fabric construction, air permeability, you name it. All these effects are going to be seen as one number, and you're not able to discriminate what is the effect of the PCM versus the other properties that you have. And particularly where you see that in comparison of sample A and B, where even though sample B has a much higher level of PCM chemistry, it still shows up as a lower number. So this is showing you that these other properties are contributing much more so than the PCM in this measurement. Now, in the past, people have done a number of looked at calorimetric methods, and there's a pretty wide range of these. Differential scanning calorimetry, or DSC, is the most commonly used method for this. And what you're basically looking at is how much heat is absorbed by a material as you change the temperature over time. Given that that is exactly what you're looking at with a PCM, which is how much heat is being absorbed, this obviously is very well suited for doing this type of measurement. The type of information you can get from this method is melting temperature, what temperature does it crystallize. So if we think back to the slide where I'm talking about the active effects of thermal management, here you could look at what temperature is the heat absorbed, and at what then with crystallization, at what temperature is the heat released. You also have the enthalpy of fusion, that is how much heat is being absorbed. Now we looked at a number of different analytical methods to see, calorimetric methods to see how they could be used for analyzing PCM on fabric. And as you can see for this, in this middle column, where I'm comparing how much heat is absorbed relative to how much we would expect to be absorbed, the theoretical, based on how much PCM is being applied. And you can see here that the variance was just was absolutely all over the place. We saw from where no PCM could be detected to well over 100% was being detected. So simply using standard calorimetric methods without being attentive to the fact that you're dealing with a PCM treated fabric, you basically get a random number generator, and it's not much value. This slide here, I basically won't touch on given time, but provides a summary, and as you look at the PDF, will recap a lot of the points that I've made. Now, what Alexiom then saw was that because we could not identify a viable analytical tool to help our customers understand how to use PCM on textiles, we went about developing a method ourselves. And what we basically did was take an established DSC method, but identified what are the core principles that need to be used to provide reliable quantification of the cooling capacity of the PCM treated fabrics. Sorry about that. So what I've touched on here is basically trying to educate, what was it that we found in our research that can help guide people in doing these studies. First, obviously, we have to start with a temperature that is well outside the melting range of the PCM. You need to make sure that all that PCM is in its active form, so that when you do the test, it can be you can quantify that. A key thing also is that you have to minimize the amount of air between fibers. I think this is a key problem from the previous data that we saw with calorimetry. A basic assumption of doing calorimetry is that you're going to be able to have good heat transfer between your sample and the instrument. If you've got a lot of air, because this is a fluffy textile sample, then you're going to have very poor heat transfer, and that's what ends up giving these low numbers where we're seeing 0% of PCM. You obviously need to have to look at a wide range of samples and be careful for contamination and understand what type of effects humidity and temperature might have. Now, here is a general description of the test method. Because of what we described previously, this is basically just putting into protocol the principles that I described on the previous slide. Important thing to see here is some basic, I'd say it's a scanning procedure that we looked at. And you can see that for looking at a PCM that would melt at 28 degrees C, we start very low, starting at 0 degrees C, and then go well beyond that 28 degrees C mark up to 40 degrees C. This will allow you to make sure you get all the signal that's associated with the PCM, and also make sure that you get overall signal. Your signal to noise is very good. Now, on the next slide, this shows you how we were able to measure the relative PCM application as we change the add-on for a given type of fabric. And you can see here, obviously what we're looking for is a linear response. And as we increase the add-on from as low as about a 12.5 to 13% add-on to as high as a 38% add-on, you get a nice linear response for this fabric. For context, it is worth saying this is a polyester-based fabric, and the chemistry was applied through a pad application. Now, what you see on the x-axis that we said, that's the add-on. If you look on the y-axis, just to touch on this briefly, I'm looking at how much energy is absorbed per mass of fabric. So you're going to need some reference when you're doing this type of study, whether you're looking at it, how much heat is absorbed relative to a given area of fabric, or perhaps for the, as we've done here, mass of fabric. For all of our tests, that's what we do here. This next slide just gives you a sense of what the data looks like coming from the DSC. And most importantly is to look at the two different sample sets that we ran here. You can see that we have, for sample set 1, we have 5 different samples. The range of values is from 30 to 35 joules per gram of fabric, which gives us an average of 33. We then took the exact same fabric, did different sample preparations, and you see here, after averaging those values, we get to 32.1. So the resolution that this method provides is very good. As a point of reference, I would say that anything in the range of, I'll say, 0 to 5 joules per gram, I don't think you can readily detect that with your hand. It's something that there's going to be subtleties to it, and it's just not something that you could readily distinguish by feeling it. So there's a lot of value in having this analytical method to help understand in a quality control sense that you're well within the level of what your consumer could detect. Typically, once you get from the 5 to 10 joules per gram of fabric, that's when you begin to significantly see a difference. And anything greater than 10 joules per gram would just be grossly different, and anyone could discriminate that. As a point of reference, we also looked at some different fabrics, so you can see the effect of that. Here on the left is a more standard woven polyester. You can see again applied through a pad application. You can see we get a linear response there. Also have the effect of what we're measuring here for the with cotton. On this next slide here, this is showing a back-coated application where this is these were all applied through a knife coat. And you can see that it doesn't depend on using a pad application, that any type of application method, you can still use this technique to show how as you increase the add-on, you're going to get a linear response with the for the amount of PCM. So the key thing to realize here is that this test method does allow you to discriminate exactly what is the PCM doing. And I'm sure a question that someone may have asked or has at least thought of is, I agree with that, but we also need to understand the information from the guarded hot plate, information from thermal effusivity, and that's 100% right. Whether you're looking at the EC method that Alexium has developed or looking at the guarded hot plate, they both are different perspectives on what exactly is that on that fabric doing, and both need to be brought into need to be taken into consideration. Really thinking about final product design. Now on this last slide here, I've shown an analysis we did for one of our customers where we have the Alexium treated pillows and we compared them to 5 different retail pillows and looking at what is the relative cooling capacity of our pillows versus what is out there on the market. Importantly, I want to note is that you can see that the y-axis here is joules per meter square. So that is actually looking at how much heat is absorbed per unit area for the area of the pillow. Given the different types of construction of these pillows, it seemed it is the best way to normalize these to have a common reference there. But you can see that here, using this method, we were able to provide for our customer very clear product differentiation. And to be able to get to this level, you know, as the title says, how do you set your company apart and the products that you're making? Having the analytical tools here are really key. And you know, the best way I would explain it is that to date, PCM applications to textiles have really been about aesthetics, about that cool to the touch effect and some measure of thermal regulation. But to be able to have quantifiable data that allows you to show how well your product performs versus others in the market, I think there's a great deal of value in that, and is absolutely the direction that we're going in. So in conclusion, we discussed how PCMs provide an effective means of minimizing how heat flow changes the temperature of the material. Also, how does it impact the cooling effect that you have for that? Over the past 10 years, PCM applications on textiles have grown significantly in a number of markets. This has largely been driven by work in the bedding industry. I think it's worth saying that given the unique properties of phase change materials, I think we're really only seeing the first steps in terms of different type of applications and what type of markets that they could be of benefit. We then looked at what type of analytical methods were established to measure the enthalpic cooling of the PCM, and looked at how, you know, basically the established methods really were not reliable at differentiating the effect of the PCM, and that really what happens is due to the other attributes of the fabric, and that which changes as a function of adding the additional binder, simply having shrinkage of the fabric through the application process. All of this is going to come to bear with standard thermal management methods. Finally, we talked about the EC method and that Alexium has developed, which we used as a tool to guide quality control, marketing, and product design when using PCM materials on textiles. We see this as an invaluable tool, and it's been critical for all the work that we have going forward. And we're happy to work with people to help them understand it, because I think once the market starts establishing metrics, as you see with other technical textiles, you're really going to see significant improvement in product design, and we'll see these markets continue to grow. So with that, I'll leave that for questions, and if anything we can't answer here, given the time allotted, you can feel free to contact me through the email address listed here.
Thank you, Dr. Brookins. Again, if you have any questions, please submit them in the questions box on your control panel. We do have one question. Is the market share chart specific to a paraffinic materials or all PCM types?
That is for all PCM types. And typically, when you're looking at these different markets, such as for transportation and cold chain transport, they typically would not, from what I've seen, don't rely on paraffinic materials. So that does represent a wide range of different PCMs, and but anything in the anything around textiles would typically use paraffinic, as we described.
All right, thank you. A next question that just came in is, what is your suggestion if a brand wants to claim cooling effect on a PCM treated textile product, and then how to substantiate the claim?
I think that is it really depends on whether you're looking at comparing yourself relative to a competitor, or whether or not you're simply making a claim for the product itself. In terms of competitor, I think you have to take in consideration, the kind of any legal issues that might be associated with that, and you have to make sure you're on very firm grounding. And I don't think I would be the best person to provide that guidance. In terms of just making the claim about what your material itself is doing, and that what your PCM application is doing for you, it really does come down to analytical tools, and how do you represent those numbers. What we have focused on with our method is how much heat is being absorbed. I think that is absolutely critical to the cooling effects that are perceived, and is something that is readily quantifiable. In terms of as you move into the other methods, as we discussed, it really just has to be taken in a balance. But it really just comes down to the data, and what you can demonstrate with your products.
All right. Another question is, you mentioned yarn infused with PCM made by Outlast. Are you aware of any others?
I actually am not. I know that for some applications, that is more viable in terms of minimizing costs. You don't have the processing, and I'm a bit surprised that you haven't seen others. But no, I'm actually not aware of that, and that could be due to patent issues, or it could simply be due to capabilities in terms of what people are able to do through manufacturing. It's not something I've looked into, but I agree with the person who asked the question. I'm not aware of any other products or manufacturers of that.
Okay. Another question is, have you seen any PCMs introduced into films?
Into film?
Yes.
I have not. Basically, I have not. I mean, we've seen, when describing a film, I guess what they're asking is integrating the PCM into a film type structure. I haven't seen that. I've seen, a comparable effect might be achieved by using a scrim, and that we've seen some of, but not as a film. I think that given the it depends on how thick the film is, but given the particle size, that could be a challenge. Also depends on how much you want to dilute out the PCM, but the problem is, by achieving good film quality, you're then diluting out the PCM, and you're not getting the actual property that you're looking for. So, but yeah, I'm not familiar with that.
Okay. And then another one is, how long does the cooling effect last?
It depends on the construction, obviously the level of the PCM that is added, as well as the fabric properties. I think that you can see for some PCM applications I've seen where it seems to be for competitor products that we've looked at, that can be exhausted within 5-10 seconds. I think that for we typically are working applications where you're doing much higher PCM loadings, and we see those effects last for anywhere from a minute or two if you're talking about the cooling effect where it starts to tail off then. In terms of once you get into thermal regulation, where you're looking at how does the PCM control the temperature of the environment, there you're looking at steady state effects. And so you're saying that given, assuming your environment's not changing, that the PCM effect is almost say permanent, but is constant. So for cooling effects, it tends to dissipate from I would say within a few minutes at most. And then for thermal regulation, it'll be more long term.
All right. Another question that came in is that if treated on a mattress ticking, does the PCM effect work through the sheets?
It does. You can have multiple layers of materials and still have that PCM effect. It does not. It is not limited by. It is. I would say that this way. The impact of that coolness will be mitigated by having that additional layer. But we've worked with customers where we're adding, specifically putting a PCM onto one layer, then have a different fabric on top of it, and you will feel that PCM, the cooling effect, immediately. If you were to go to more than one layer on top of the PCM, the cooling effect, that cool to the touch sensation, would be reduced pretty significantly. Obviously, you have air there, which in those different layers that will provide some insulation. When you're dealing with thermal management and you're looking for PCM to help draw heat away and to act as I think of it as a buffer in terms of the total thermal profile of this, of the material here. We're talking about a mattress. The use of multiple layers can be an advantage or a disadvantage, and doing proper design will then help. And I would not be worried about having more than one layer when you're talking about thermal management. It would really come down to the overall construction of the system.
All right, thank you. It looks like we have time for one more question. If you need to laminate to a PCM treated fabric, what is the best treatment method for a good lamination strength?
That is a very good question. It's not something I've ever had someone ask. I would think if you're wanting to laminate, my initial thought might be spray, so that you can have better texture and get some good physical entanglement between your laminating, the layer you're laminating with, to what you're laminating to. I think that beyond that, you're dealing with what type of binder that you're using and getting your laminate so it has good chemical interaction between, not a reaction, but just kind of interaction. What is the interface between those two materials? That would drive the quality of the lamination better than anything. I can say that when you're doing a knife or screen coat of a PCM, as what we've typically done, you're going to see it's going to be a very smooth surface, and it probably would not be rough enough to form a good interface, strong interface.
All right, well, we are out of time for today. Thank you all for your questions, and please feel free to reach out to the ATP staff for more information on the division and its programming throughout the year. IFAI Expo is also quickly approaching, October 15th to the 18th in Dallas. Register today to participate in a full day of education and a robust show floor featuring testing demo zones and e-textile workshop. Registration is open now at ifaiexpo.com. Finally, thank you again to Dr. Brookins and Alexium, and thank you all for attending.